Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Welcome. This is Mr. Simon, and we are going to be studying Senior 5 Chemistry. And we are on unit number 11, that is solution and titration. And our lesson today, we are going to talk about iodometric titration. Iodometric titration. Sometimes we call it thiosulfate titration. So quickly. So the objectives of this lesson is by the end of this lesson, you should be able to carry out calculations involving iodometric titrations. So someone may ask you, what is iodometry? Actually, iodometry is a type of titration which involves two substances. Normally, we have two main substances. One of the substances is the iodine. That's why sometimes we call it iodometric titration. Another one is thiosulfate, and that's why we call it thiosulfate titration. So in this experiment, we normally use excess of potassium iodide. So that's why sometimes we may call it somehow back titration. Back titration. When you talk about back titration, you easily discover that this is a kind of back titration. But you can also call it a redox titration, because if you look at our equations, as we have said, we have two substances basically involved, iodine and thiosulfate. So if you look at your screen very well and recognize our equation, that is iodine changing to iodide, that is reduction. And the thiosulfate changing to tetrathionate, and that is some bit of oxidation. So we can call this type of reaction, or this type of titration also can fall under redox titration. Redox titration. So we have many redox reactions which we are going to be looking at. Let's first illustrate the one of them, the first one. This one, which is very important among them. So basically, everywhere you're going to see that actually we have iodine being changed to the iodide ions. Iodide ions. And then we have thiosulfate. So how can we balance our equation? I think we put 2 here. And we can call this one reduction. Then we have this one, 2O3, 2 minus, which will give us this one, 2 minus. So we balance our equation. So observe here we have 4 electrons. So to make this side 4, we add also 2 electrons. So we can add them. We can add them. So as we add, we cancel out this. So we shall have iodine, hence iodometric titration, and plus 2. So giving us plus minus. So that's what we have. So this is our equation. If you look at it, it's redox. Reduction, oxidation. Reduction, oxidation. But we are also going to see very many other equations. Very many other equations. For example, copper. If you remember this equation in our senior 4 work somehow. So if copper 2 sulfate or copper 2 ions reacting with the iodide ions, ions here, and they give you copper 1 iodide and iodine. So if you recognize very well the iodide ions here, the iodide ions are being oxidized to iodine. And then the copper 2 is being reduced to copper 1. Hence redox reaction. Then here we also have potassium iodide with acidified potassium iodate. The equation has been balanced. It also involves here oxidation and also reduction. Then we have this one also iodine, which is oxidation and also reduction. Then we have this one also of a reaction between potassium iodide. Potassium what? Iodide. The reaction between potassium iodide and acidified potassium dichromate. So in our previous lesson, we have looked at this. So it's an example of a redox what? Reaction also. So you'll observe that in our equations, we shall always have two types of redox what? Reaction. We shall have this one and one of those ones you see on the screen. So quickly, let's continue. So in this titration, we use starch as our indicator. Starch as our indicator. So in case we are adding, for example, if we have excess of iodine, excess of what? Iodine. Our endpoint will be blue-black, as you see in our diagram. If you look at your screen very well, you can see the blue-black. Then sometimes the blue-black color disappears or changes to colorless. So when you have excess of thiosulfate, that means when we have a little bit of excess of thiosulfate, when almost all the iodide ions have disappeared, then iodine has, when almost all iodine has disappeared, we shall have colorless of thiosulfate. So we shall do this in the laboratory. So let's just continue. So we are going to look at an example. As you've seen, one of the objectives of our lesson today is actually we are calculating, we are involving calculations in this what? In this type of titration. So as you've seen, we have excess of potassium iodide, which makes it back titration. Then we have copper 2 reacting with iodine and thiosulfate reacting with iodine. Then that makes it redox. But specifically, because we have iodine and thiosulfate, we can call it iodometric or thiosulfate what? Titration. So the first thing we are going to do is, because thiosulfate is used in this experiment, so how can we standardize this thiosulfate? So we are going to just look at some of the things we can use to standardize thiosulfate. But this time, we are using copper sulfate. We are using copper sulfate. So standardization of solutions. So let's look at this example. It says that in order to determine the concentration of sodium thiosulfate, excess potassium iodide was added to 25 centimeters cubed of 0.1 molar copper sulfate solution. The iodine liberated was titrated with sodium thiosulfate. So recognize in our equation, we have ionic equations. So if you recognize very, you'll observe that copper is reacting with excess potassium what? Iodide. And this iodine which is evolved, which is what? Evolved. Normally we have an observation here. Things, we have some brown, yellowish colors because of formation of copper 1. So here after, actually this is one of the chemical tests of copper 2. We have formation of iodine and copper 1, which is normally brown. Or some people call it reddish brown. So again, you'll observe that as you're carrying out the experiment. Then after, you'll add your starch indicator. Then it will change to blue-black. Then you titrate with sodium thiosulfate. You titrate until when it changes to white. Normally it is white color. It has that white appearance. Or we can call it colorless at our end point. So you see this time iodine is what? Disappearing. So let's see how we can calculate the mass. When they say calculate the mass of sodium thiosulfate dissolved in 1,000 centimeters cubed of solution, it means they are asking us to calculate the concentration in grams per liter. So let's quickly go to our calculation. So our first thing we are going to talk about today is standardization. Standardization of solutions. Standardization. So we begin and we say, we are going to begin with copper sulfate because we have the moles and the volume. So we say moles, can say moles of copper 2 will equal to, so we can use this thing and say molarity V over 1,000, or we can use MV. So our molarity this time is, our molarity will be 0.1 times volume, which is 25, divided by 1,000. So we shall get we shall have 2.5 times 10 to the power negative 3 moles. Hope you have your calculators nearby. Our topic, as we have said, is all about what? Calculation. So I have got my calculator being ready for calculating. So the next step here, now we have moles of copper. So we can say using equation 1. And say using what? According to our question, we can call it equation 1. We can say moles now. We can say moles of iodine. Moles of iodine, which has been produced by copper. So using mole ratio, we can use mole ratio, and then we'll be able to get the moles of what? Iodine. So this will be a half, 1/2 times 2.5 times 10 to the power negative 3 moles. So our value here, people who know mathematics, will be 1.25 times 10 to the power negative 3 moles. Then from there, we move to the second equation, using equation 2. Using equation what? Equation 2. Using equation 2. We say moles of thiosulfate. Moles of thiosulfate. So this time we are going to multiply by 2. We say 2 times 1.25 times 10 to the power negative 3 moles. So our answer will be 2.5 times 10 to the power negative 3 moles. Then from there, the volume of sodium thiosulfate is given. So we can get our molarity. You can say molarity, we can use this equation again. Molarity of thiosulfate, molarity of thiosulfate, sodium thiosulfate will equal to, we can use this one, we can say it will equal to number of moles over volume times what? 1,000. Then we shall have, can substitute in here and say 2.5 times 10 to the power negative 3 times what? Times 1,000. Times 1,000. Divided by 12.5, which is the volume of thiosulfate. So we cancel this one and this one. So we said 2.5. You can try out also to check the answers of the teacher. So our answer here will be 0.2 molar. Then from there, we want mass. We said this mass is the same as concentration. Same as what? So we can say concentration, if you remember very well, in grams per what? Per liter. So we can use this formula which says that number of moles. We can help ourselves with this formula which says that number of moles is equal to mass over molar mass. So our mass will equal to number of moles times molar mass. So it means we need to find the molar mass of our sodium thiosulfate. So you recognize that now we want mass in 1 liter, which is concentration in grams per liter. Then we have moles in 1 liter, which is molarity. So concentration in grams per liter, which is mass in 1,000 centimeters cubed, times molar what? Mass. So we shall have 0.2 times the molar mass of sodium thiosulfate. So recognize that sodium thiosulfate is actually, we say sodium times 2, which is that is plus sulfur times what? 2 plus. Then oxygen, which is 16 times what? 3. So our value of molar mass of thiosulfate will be 158. So we multiply and say times 0.2. So we shall have our value 31.6 gram per decimeter of sodium thiosulfate. So after standardizing your sodium thiosulfate, you can use it for another calculation. You can use it for another what? Calculation. So that is our answer. So that's our answer. So let's quickly continue to the next question. So now we have another question where we can use thiosulfate titration to find unknown molar masses. Unknown molar masses, yeah. So we can put a title, say finding unknown molar masses, yeah. So if you look at our question very well, you recognize that we say a solution of sodium. This thing is similar to something we know, which is sodium. Let's not say it is that one, X. I say exonate, or X or what? Yeah. So was made by dissolving 1.6226 in grams in 1 liter. Then 25 centimeters of this solution was added to excess acidified potassium what? Iodide. So the iodide ions produced reacted with 24 centimeters cubed of 0.05 sodium thiosulfate. Using these equations, they have given you the equations. They tell us to calculate the number of moles of thiosulfate. Number of moles of what? Thiosulfate. So we can quickly attack our question, which says that they want moles of thiosulfate. Moles of what? Thiosulfate. So we have MV over 1,000. So we shall calculate, and we have actually molarity 0.05 times the volume, which is 24.6 over 1,000, which will have, so we have here 0.05 times 24.6 divided by 1,000. So our answer will be 1.23 times 10 to the power -3 moles. Then from there we calculate the moles of iodine. So we can say here AB, we can say using equation. So we want now using equation 1. So we have thiosulfate. So we say moles of what? Iodine. Moles of iodine. If you want to get the moles of iodine, we are going to say 1/2 times 1.23 times 10 to the power -3. So we're going to divide by 2. So we shall have 6.15 times 10 to the power -4 moles. -4 what? Moles. Then from there, another question is telling us to calculate the moles of what we call the exonate this time. So number of moles of exonate. So we have this time we are going to transfer this iodine to the equation number 2. So actually, this one is equation 2. Let's call this one equation 1 from our question. Using equation what? 1. So we say moles of, we say exonates. So we have this will equal to number of moles will equal to, so if you want to get that, so we can use mole ratio. If you have a problem with the mole ratio, you can do like this. You say iodine and this one. So we say, now we have iodine, So we say we have 6.15 times 10 to the power negative 4. Then here we have x. We have what? X. Then here for iodine is actually 3, and this is actually 1. So if you want to get x, obviously recognize the cross multiply. So our x will equal to 6.15 times 10 to the power negative 4 divided by 3. Divide by 3. So we divide by what? 3. So we have 2.05 times 10 to the power negative what? 4. Negative 4. These are moles of this one. So after getting it, we get the molarity. We get the molarity. Hope you are following and you're enjoying our lesson. So we have molarity of this one will equal to number of moles over volume times what? 1,000. So we have the moles times 10 to the power negative 4 divided by the volume. So our volume was given with 25 centimeters cubed of this solution times what? 1,000. So we shall have times 1,000 divided by 25. So we have something like, you can say 0. Or we say 8.2 times 10 to the power negative 3, which is our molarity. So we'll get the molar mass. The molar what? Mass. Molar mass. So our molar mass of sodium hexonate, so we can try to do it here. If we want to get the molar mass. So we can borrow this one. What we have done here, this expression we have here, we can say that molar mass will equal to our concentration gram per liter over divided by molarity. So we have 1.6226 divided by molarity, which is this one, 8.2 times 10 to the power negative 3. So our answer will be, we say 1.6226 divided by this one. So we have our value as 198.97 gram per watt per mole. So from there, this is E, this is part E. So from there, we can be able to get our last part, the value of X. So part F, which is value of what? X. Value of X. Value of X, we say that sodium hexonate. Okay, so this sodium, we are going to say is 23 plus what? X plus 16 times what? 3 will equal to approximately 197.87. So we calculate again, we say, so we have 23 plus 48. So our X will equal to, so 23 plus 48 minus 197.8 what? 7. So we shall have approximately 127. So it is easy even to recognize that actually our X is what? Iodine. Is what? Iodine. So that is our question. Hope you followed very well. So you can look at the answer and you appreciate it. Quickly, let's talk about let's talk about our exercise. Let's talk about our exercise here.